In this video, I will show you how to construct the efficient frontier curve and capital market line for 5 assets. In this way, so you could see the daily share prices for 5 stocks or assets. Company 1, Company 2, Company 3, Company 4, Company 5. Then we've got the date from the start date, which is 6th of January 2022, down till the end date, which is 5th of January 2023. So for 1 year period of time. In other words, the sample size is for 1 year. And because we're dealing with daily observations, we'll consider the fact that 252 business days makes up a year in finance, excluding bank holidays and weekends. So here is the sample we've got from the start date to the end date. In this case, we could take more observations by increasing the sample to other years. All right, so we'll work out the daily returns in this case. As you could see from my previous videos, how to work out the daily returns. And then also, we've computed the annualized mean and standard deviation for the 5 companies. We've also computed the variance covariance metrics. And the next task is to compute the volatility or the standard deviation and the expected return for the portfolio, together with the Sharpe ratio. This is what we want to do just before we move on to the main task, which is to obtain the data points for the asset weights. That is the weight for the company. In this case, we're going to have data points in the first case, second case, and so on. That will be sufficient enough to compute the volatility and the expected return, and also the Sharpe ratio. So, of course, we will use the volatility and the expected return data points to construct the efficient frontier curve. Then the information about the Sharpe ratio will also be helpful for us to construct the capital market line. All right, we'll come back to that. This is what we want to do. So the first assumption, like it's already done here, is that we assume that the assets are equally weighted. So they have the same weight, the same proportion of investment. So in diversifying the portfolio, in this case, the mean variance portfolio investor assume that the investment in terms of the proportion should be the same. For instance, investment in company 1, company 2, up to company 5 should be equal. So in this case, how many companies? We've got 5. So if you work out, that means you've got 1/5. And this gives us 0.2. That's why we've got 0.2 all through. And then the sum should be equal to 1, which is this. So this is the sum of all this. 0.2 times 5 will give us 1. Or simply sum 0.2 plus 0.2 till this last value, it will be equal to 1. So that's fine, from which we computed the standard deviation, which is the volatility of the portfolio and the expected portfolio return, and the corresponding Sharpe ratio. So this has been done. We'll consider the value of the Sharpe ratio is relatively small. It could be higher than this if we optimize. In a situation where you want to suggest as a consultant to a client, let's assume your client is an investor and your client wants a strategy that will enhance higher profit or that will have a guaranteed return, a guaranteed higher return, that is in this case to have a higher expected return at a lower risk. So that's what we're actually looking at now. So in the first instance, we're going to do the same here for the optimal portfolio or risky weight. Rather than investing equally, in this case, the same proportion of investment, you want to work out a strategy whereby you could advise the investor to invest in different proportion. Because if the investor could invest in those companies that could have a higher guarantee in terms of the expected return, positive return, then it is advisable to invest more in that company rather than investing equally. So that's the strategy, that's the idea we got here. So to do this, what are we going to do now? We want to work out. So first of all, we move on to this point. So here will be 0.2. We've got 0.2. It shouldn't be in formula form, so enter it manually. 0.2, 0.2, and the last value 0.2. So all is 0.2. Then next is to take the sum like we've done for the equally weighted before we proceed to use the Excel solver in Excel to optimize. So here will be the sum of this portfolio, this asset weights, the sum of the asset weights, which is equal to 1. So we're happy with that. Next, we want to compute the standard deviation. And here it will be in matrix form. So if you go by the formula, then this is what we want to do. So what we simply have is the square root of the transpose of the weight times the variance covariance matrix, which is a semi-positive definite matrix times the weight. So W transpose SW. That's what we want to do now. But in Excel, this is what we will do. This will be equal to the square root, in parentheses, matrix multiplication, in parentheses again, matrix multiplication, in parentheses, transpose of the weights. And then the variance covariance matrix. So all these values. This is a 5 by 5 square matrix. Close the bracket, comma, and then the weights again. Double close the bracket. Enter. So we've got the result. If you look at this, you'll see that it's exactly the same because we're still replicating the result for the equally weighted. Next is the expected return, which by formula is this. So the expected return, the expected portfolio return will be the transpose of the weight times the return for the 5 assets. So it's also in vector form. So you could see the transpose of the weight, which is this, and then this is the return, also in vector form, R1, R2, and so on till R5. And of course, this will be feasible in terms of matrix multiplication. All right, so we'll go back to our spreadsheet to compute this in Excel. So this will be matrix multiplication, transpose, in parentheses, of the weights. So these are the weights, comma, then multiply by the expected return, which is this. That is the mean for the asset. Remember, there's difference between the expected return for the portfolio and the expected return for the asset. So these are the expected return for the individual asset. In other words, the mean of the asset. Company 1, company 2, and so on to company 5, there are various means. But for the portfolio is the one you're taking overall. All right. So this is what we've got. Close the bracket. Enter. So we've got the value. And then the Sharpe ratio. What is the formula for the Sharpe ratio? The Sharpe ratio have this formula. SR is equal to the expected portfolio return minus the expected risk-free rate over the standard deviation of the portfolio. So this is the formula for the Sharpe ratio. And we expect the Sharpe ratio to be high, where possible above 100%. So it should be above 1 as a value. That's better, but when it's below 1, it doesn't really look good. All right. What do we do in this case? So the higher the Sharpe ratio, the higher the expected return. That's what we expect. Let's go now to the spreadsheet using this formula where we've got expected portfolio return minus the expected risk-free rate over the volatility or the standard deviation. So we work this out. This will be, in parentheses, what have we got? The expected return, which is this, minus the risk-free rate, which is this. Over the standard deviation. Enter. So we've got the value. You could see here is approximately 32% as a Sharpe ratio, which is the same as what you've got here, because we're still working on the equally weighted in the first instance. So now we're done with the equally weighted. An investor might not be happy in this case that, of course, we cannot really see a better guarantee. What if we change the strategy whereby we can have different proportion of investment? Let it not be that you invest equally in diversifying the portfolio, diversifying your investment. We want to invest in different proportion. So in this case, it will now take us to the optimization part. So what you do, we now think of here, in this case, you need to do some kind of reasoning. If you look at this, you will see the expected return is 0.0976. And then you could see the Sharpe ratio is 0.31704. The standard deviation of volatility is 0.22899. So when you look at this, you could see that you could have values a little bit below the expected return and values above this expected return as a data point, or as a range of value rather, that you could use to obtain the data point. So we want to use this option. There are other options one could use to obtain the data point for the weights, but we want to use the target return option. In this case, you could look at values that are below 0.0976, and then you could have a scale where it could be increasing, and it could be increasing gradually until it will be above and get to maximum. Then we stop at that point. So in this case, we want to use 0.08, which is below 0.0976. Then I want to be increasing it by 0.02. So the difference between the first and the second should be 0.02 and so on. So if the next would be 0.10 and so on. Now let's see the difference. If I say this minus this, the result will be 0.02, which is okay. So I'll be increasing it in this way. So to work this out, this is what I intend to do. I'll simply move to this point, and then here, to obtain the data point, here is the expected return. So I have 0.08. I move to the next, 0.10. Then plus 0.02 will be 0.12, plus 0.02, 0.14, plus 0.02 will be 0.16, and so on. So let's just stop at this point first. Then I'll use this to show us, and then bring in the rest. So this is what we're going to do. We want to set from our optimization, we make sure that the expected return should also be included as a constraint, where the value should be 0.08. And based on those values, copy what you will have as the weight suggested by the Excel solver, paste them in transpose form, also paste the standard deviation, expected return, and the Sharpe ratio, which are the corresponding values you obtain by using the proportion of investment suggested by the Excel solver. And you will repeat the process over and over for the target return. So you will only be changing the target return. So in doing this is what we're going to do. We simply go to the Excel solver. So go to the top icon, and in the top icon, what you need to do is to click on data. So click on this data, and at the top right-hand corner, you will see solver. Then click on the solver. Now, if you got values in already, you can reset. So reset all, that's fine. So that it will be empty. Now we want to start. So what we want to do is this: set objectives. So we maximize. Maximize what? We want to maximize the Sharpe ratio. If the Sharpe ratio is maximized, but if you choose to minimize, then you are minimizing the volatility, which is the standard deviation. We minimize risk and maximize the Sharpe ratio. Then by changing, remember, maximize the Sharpe ratio by changing the weight, because it's the weight you want to optimize. You want to see that it gives you a suggestion regarding the proportion of investment while diversifying the portfolio. So in this case, we have by changing weights, then constraints, add constraints. So in adding the constraint, what do we do now for the constraints? The first constraint is that the portfolio weight should be greater or equal to 0. So we use this option, greater or equal to 0. That's fine, because we expect the proportion of investment to be positive. It shouldn't be negative realistically. So from a realistic point of view, your proportion of investment should be positive and not negative. Though in some situations, you could even have negative values just to have your data point, but a realistic point of view, we expect it to be positive. All right, having got this, you move to the next stage. You want to add another constraint. The other constraint is that the sum of the portfolio weight must be equal to 1. Please, this is necessary. You must add this constraint. Otherwise, you might have negative portfolio weight. But don't let that bother you. Sometimes you could also have that, depending on the nature of the optimization problem, in order to have feasible data points that will enable you to construct the EFC and the CML. That is the efficient frontier curve and capital market line. So that's fine. We've done this. Okay. And then we want to add the target return. That's very important. So add the next. The next constraint will be this target return. And we set this target return to be equal to 0.08. So that's fine. 0.08, because we want the range of values to start from 0.08. And then we go down until it will get to a maximum point. We'll stop there. All right. Solve. So you could say now we obtain the solution. So you now see the weights that we obtain from the Excel solver. Copy these weights and then paste them here in transpose form. Also, copy the standard deviation and the Sharpe ratio. Now, you might decide to paste in values form here. Sorry, you paste in values form, and then you can now copy again and paste in matrix form if you want to do that. You could also use other tricks to do it, and it will work out fine for you. But if you paste in the formula form, it might not work, I'm afraid. So that's fine. So we have the values. Now, the next again is to set your target return to be 0.10. You will only be changing the target returns at this point. So long as you use an appropriate scale or range of values for the target return, you will be changing the target return as a constraint. All others remain the same, and you will see that your your asset weights will be changing until it will give you sufficient data point that it could use to construct the efficient frontier curve and capital market line. So that's fine. So we'll move on to the next stage. We'll go to our optimizer again. And then we change this. So change this to 0.10 and solve. And here you go. This is the result. So you could see the result. That's fine. Now copy this. And then you paste them in transpose form. Similarly, You want to copy these values regarding the standard deviation, which is the volatility, expected return, and the Sharpe ratio. You might paste it here. Oh, sorry. Use the value option. Copy, and then you paste in transpose form. You use other method, that's fine. We go again. The next value will be 0.12 and so on. You might write it elsewhere or save it elsewhere, but just to let you know that these are the values you'll be following until you get to the maximum. So we go again, go to the Excel solver and change the target return. Change the target return to 0.12 and then solve. Then you will obtain this result. Copy these weights, bring in here, and then paste. Similarly, you can copy the volatility, expected return, and Sharpe ratio. You copy and then paste in transpose form. You go to the next. You may take this off if you wouldn't want to be confused, but whenever you paste something new, it will override the old. So you're going again to the Excel solver. The next value after 0.12 is 0.14. So change the target return to 0.14, and that works fine. So we've got this result. Again, copy the weights and paste. So paste the weights. And then again, we'll do the same for the standard deviation, which is the volatility, expected return, and Sharpe ratio. Copy and then paste in transpose form. Next is 0.16 as the expected return or your target return. So we go to the solver and change this to 0.16. And we solve, and this gives us this result. So copy the weights and paste in transpose form. Similarly, copy the volatility, expected return, and Sharpe ratio, paste in values, and then you can transpose and paste them here. All right, so you could see this. We've done all of this very clearly. We will continue the process until we will get to the largest value. That's what we want to do. I already got the rest of them here, which I've worked them out, but continue the process. So that means the next will be 0.18, next will be 0.20, and so on till it will get to the last value. So in other words, if you follow this trend, what will be the next value? From what you can see, you could see the values are all there. You continue until it will get to a point where you will now stop when it gets to the largest value that you expect from your data point. Might still go down until at what value will you stop? That's what you are looking at. At what value will you stop? Is it 0.52, for instance? So I already got them here. So I'll simply bring what I have and paste, which I've done already. All of this is what I've done repeatedly for the other cases. So do it repeatedly like I've done for each case until you will have all this. So you could see that all has been filled up. So using that is the Excel solver. Change the target return to 0.18, you will have the data point. change the target return to 0.2, and so on till you have all of this complete. So now that we've got this, it's now easier. For instance, now, this last one, 0.52, let's see. If this is 0.52, and we solve. So you could see the result, what we've got. 0. So you could see here we've got 0, then 0.06880, 0.9312, and so on. So you could see these are the values we've got. And then you could see the expected return 0.52, which is there. The standard deviation of volatility is 0.32492, which is this. And then the Sharpe ratio is 1.52344. You could see it here. Now, the reason why we're not going beyond, let's assume you got 0.54. What will happen? There will be something wrong here because it will not be feasible. So it's always important for us to know that you need to have a range of values for a target return that will be feasible for the optimizer so that you'll be able to have a feasible solution. So now, if you go to the solver and change the target return to this value, 0.54, look at what is going to happen. If it is 0.54, solve. So you could see now, solver could not find a feasible solution. That's the reason why we do not go beyond that. Using this, our scale, from the least to the highest value of the target return. So we stop at that point because if we go beyond that, the solution will be infeasible. So we're happy with this now. The next thing we want to do is also bear in mind that you could use this formula to obtain this. You could use this formula you've got here, this, to compute the expected return, and this for the variance. And then when you take the square root, you obtain the volatility or standard deviation. So it's very easy using this. If you go by the Excel, let's assume this now for this what we've got. So if you have this equal to, for instance, if you want to work it out, okay, let me leave this as it is. I want to leave it in this way now. Let's assume, just to confirm, if you have this equal to the weight for 1 times the expected return for company 1 plus the weight for company 2 times the expected return for company 2 plus the weight for company 3 times the expected return for company 3 plus the weight for company 4 times the expected return for company 4 plus the weight for company 5 times the expected return for company 5. If you have this, that's fine, but you will need to log these values that we are bringing from different cases. That is the annualized returns for the companies. So in your keyboard, press F4. That's fine. The same for P4. So we want to log P3, P4, P5, P6, P7. In your keyboard, press F4 when you highlight it. Also, P5 in your keyboard, press F4. F4 rather. Now, for P6 in your keyboard, press F4. And for P7 in your keyboard, press F4. Enter. So you could see now, it gives exactly the same values. Drag it down up to this point. So you could see that the values for the expected returns are the same. Using the formula is still the same as using the optimizer. The same is applicable for the standard deviation. You could do that and you will have the same result for the standard deviation here. But for ease of computation, you could just copy and paste from the optimizer, which is fine. So now we want to construct the efficient frontier curve. We're nearly done. Now, at this point, you just need to highlight the volatility and the expected return. So we highlight this, and then when we highlight, what next do we do? Go to the top icon, click on Insert. From Insert, go to Charts, and then you could take this option. So here you could see the shape of the efficient frontier curve, which is a parabola. We could decide to include the axis title. So here we'll have the expected return. And then that is for the vertical axis. And for the horizontal axis, we have the volatility. We can bold it if we want. Similarly, for the title, here we could give efficient frontier curve. On capital market line. For the efficient frontier curve is the same as CML. Oh, sorry, EFC rather. EFC. And the capital market line will be CML. In other words, we could just leave it at this point. I think that's fine. The efficient frontier curve and capital market line. So this is the efficient frontier curve. Could look at this very well. The minimum variance portfolio will be somewhere here. Now, the last stage is for us to obtain the capital market line. The shape, the parabolic shape is there, which is to say it is correct. All of these dots shows that they are all feasible. So anyone outside here is infeasible. So the next stage here is for you to look at the Sharpe ratio. From among the Sharpe ratio, which one is the highest? If you're not sure, you could use this formula to determine which one is highest. Equal to maximum, then all of these values. So it will be 1.96771. So if you look at this very well, it will be somewhere here. 1.96771, which is this. So in other words, this will now be the data point that gives us the optimal portfolio. Then, of course, here will be the volatility. So this is the volatility. This is the expected return, and this is the corresponding Sharpe ratio. So this gives us the best. So in terms of proportion of investment, in company one, 0%. Company two invest approximately 35%. Company three invest 0%. Company four, sorry, company one to three. Company four, yes. Company four invest 41%, and company five invest 25%. So in doing this, there is a guarantee of higher expected return at lower risk. All right, we now want to work out, take note of this. This is the volatility, this is expected return, this is the Sharpe ratio. So to finalize this, we will now work out. The volatility will be the weight times the optimal volatility, while the expected return will be the weight times the optimal return plus 1 minus the weight times the risk-free. So we now begin a situation where we have 0%, 100%, and 200% in terms of the weight. You could use other values, but these are the values I feel it will be suitable for this kind of analysis or the data points I've got. So this will be the weight, which is this weight, times the optimal volatility. Remember, this is the volatility, this is the expected return. So times this optimal volatility, which is X26. So I highlight it, and in my keyboard, I press F4 so that it will replicate it. So we got 0, and then when you drag down, you have other data points. Similarly, for the expected return, this will be equal to the weight times the optimal return. So this is the optimal return that the optimizer have suggested for us. So multiply by this plus, in parentheses, 1 minus the weight times the risk-free rate. This is the risk-free rate. So 1 minus this value. Then what you need to do is to log these values that you're bringing from different cells. Y26 in your keyboard, press F4 after highlighting. The same for the risk-free rate you are bringing from a different case. All the ones you're bringing from different cases, you need to highlight in your keyboard and press F4 so that you will log them in order to replicate for other cases. So enter. Sorry. So now we can enter. And this gives us exactly the risk-free rate in the first instance. Likewise, for the volatility, it will give you zero risk. And then from there, it will be changing. So here, it will also be changing. And then we've got this. So the final thing we want to do now is to obtain the curve, and then we are done. So what do we do then? We'll now go to the graph. Remember, here is the optimal portfolio. At this point that you've got this is the optimal portfolio. So here, click on anywhere in your chart, right click, and then go to select data. When you select data, what do you need to do at this point? Go to add. The series name will be CML, Capital Market Line. Series X, which one is the vertical axis? Take note of that. Which one is your vertical axis? Which one is the horizontal? The vertical axis, here, you have your vertical and the horizontal. Horizontal axis is the volatility. Vertical axis is the expected return. So your X is what? Your X is the horizontal axis, which is the volatility. So you take that, and then you go to series Y, which is the expected return, the vertical axis. We're done with the horizontal axis, X, volatility. Vertical axis, Y, is the expected return. So you could see now, and then enter OK. OK. And here you go. So here you could see the shape of the efficient frontier curve and the capital market line. So we're done with this analysis. We've obtained the efficient frontier curve and also the capital market line for 5 assets. Here ends the video. So thank you so much, and thanks for watching the video. Good luck.